Hello, my name is Maria Lopez Olivo, Assistant Professor at the University of Texas MD Anderson Cancer Center. Today, I'm going to cover a lecture on decision analysis for outcomes research. This lecture is part of the knowledge synthesis module, and the slides were provided by Dr. Jackbrit Chadwell, Senior Scientist in the Institute for Technology Assessment at Massachusetts General Hospital. In this lecture, we'll cover the basics of decision analysis and modeling, including when and where such models can be used. We'll explain one specific type of modeling approach, Markov modeling, which is commonly used for medical decision making. Within that, we will cover how to capture uncertainty in models. And finally, we'll present examples of decision models in cancer outcomes research. Let's start first with a brief introduction to modeling. By the end of this part of the lecture, we must be able to explain what a model implies in outcomes research, describe the circumstances under which models may be necessary, and be able to list some types of models. As you have seen in previous modules and lectures, comparative effectiveness in research is designed to inform decisions by providing evidence on the benefits and harms of different options. The evidence is generated from research studies with experimental methods, such as randomized controlled trials, which are considered the gold standard to compare the efficacy of two or more alternatives. Observational methods, like those from cohort studies and case control studies. And systematic reviews where the evidence is synthesized. Or decision analysis that help discover the most advantageous alternative under specific circumstances. It is a quantitative approach that uses data for multiple sources. So, what is a model? The term model refers to a simplified representation of reality. We use them to replicate scenarios on a computer, either hypothetical or real-life scenarios. And when do we need them? Well, in cases where experiments may not be feasible, such as when they may be unethical, too costly, or just too difficult to carry out. For example, we cannot determine the efficacy of a parachute by undertaking a randomized controlled trial by making people jump from airplanes with and without parachutes. That would be very unethical. Or when we need to make predictions, for example, we may use models to predict the long-term effect of a new cancer radiation treatment. Or when we need help to make decisions, for example, whether to use a new clinical device considering its possible side effects. This figure further illustrates the role of models. Consider the real-world situation where we have a problem that needs to be evaluated. This is presented in the bottom part of the figure. The ideal way would be to experiment with several ways to find an optimal solution. But here, the experiment is not feasible. So what do? We go to the world of models for assistance, which is presented in the top part of the figure. So the problem in the real world is first mapped to its model in the world of models, a process called abstraction. We then use analytical methods or simulation to arrive at the solution in the world of models. This process is captured by optimization of some features in the model. The optimized model is then mapped back into the real world as a solution. We just talked about instances when we may need to use models. Now let's talk about why we may need models. Models may help us understand the effects and outcomes of various interventions before we even implement them. If models can help us have an idea of the possible effects of an intervention, you will agree that it may be a cheaper way of finding those out than using a randomized controlled trial, so it may be cheaper using models than randomized controlled trials. Models can help in generating evidence in support or against a hypothesis. This will help the investigator have an idea about what to expect in reality. In short, Models can help us evaluate various what-if situations. Decision modeling is used in predicting the outcomes of decisions in the real world or in reality. It involves using a hypothetical cohort to replicate real-world scenarios. We may include quality of life measures as well as costs in the models. Decision modeling can integrate multiple sources of information to answer complex questions where no studies are available to provide answers. And finally, decision modeling could be used to estimate long-term outcomes beyond what is typically observed in randomized controlled trials or observational studies. For example, a new radiation treatment for cancer may have long-term effect beyond the duration of the study and will not be seen at the time of the trial. Decision modeling may be used to estimate the probability of the effect occurring several years after the treatment. Models can be categorized in several ways. Let's take a look at some of them. Models may be static or dynamic. We'll describe this in the next slides. Or they may be population-based or individual-level models. Models may be deterministic or stochastic. When we talk about deterministic models, we mean models in which the outcomes are precisely determined by a relationship between the parameters in the model and by sets of previous states of these parameters. That is, if we put in a set of given parameters, we will always produce the same output. In a stochastic model, various parameters are not described by unique values, but by probability distributions. Therefore, there is some randomness in the output produced by given parameters, as one would expect in the real world. Models may also be described as continuous or discrete time models. As the name implies, in continuous time models, time advances continuously, and different events can happen at any time, such as progression of disease or death. In contrast, in discrete time models, time advances in discrete steps called cycles. Any events of interest can only happen either at the beginning or at the end of the time period. Now let's take a closer look at some of the model types mentioned on the previous slide. We'll first discuss differences between static versus dynamic models. Static models are usually applied to single cohorts. The disease status of an individual in the cohort does not affect that of other members of the cohort. For example, cancer progression in one person does not influence the risk of cancer in other persons. These models are relatively simpler to construct compared to dynamic models. Dynamic models, on the other hand, are usually applied to multiple cohorts. Here, the disease status of one member influences the status of other members. For example, one's risk of getting flu depends on how many other people in his or her surrounding have flu. So dynamic models capture such interactions. Another feature here is that indirect effects change over time. Models can also be categorized as population-based. A population-based model keeps track of populations of individuals. These may be, for example, populations of people susceptible to some conditions or populations infected with some particular disease-causing agent. Population-based models are made up of mutually exclusive groups, and within each group there is homogeneity. That is, there is more resemblance within members in the groups than with members of other groups. Among each population, there could be subdivisions along the lines of, say, age, for example, for those under 50 years and those 50 years and older. Sexual activity, for example, those who are sexually active versus those who are not. Or location, resulting in spatially separated populations of the same species that interact with each other as individuals members move from one population group to another. These constitute what we call metapopulation or patch models. Now, let's look at individual models. You will recall that in the population-based models, we talk about various population groups, with groups being mutually exclusive. with homogeneity within groups, and that each population group could be subdivided along the lines of certain characteristics. Well, individual level models keep track of individuals within a population. In this model, each individual has an identity and a health state or some states. Different characteristics of a state can include age, sex, partners, whether one attends a daycare, and so on and so forth. These characteristics of individuals are tracked over time. Some of the characteristics, such as disease stage, may change as individuals get well or die, while others, like sex, will not change. The following models can be characterized as population-based models. Markov cohort models. Typically, these models are static. Another type of population models is compartmental models. In contrast to Markov models, compartmental models are dynamic models. In the next section, we will take a closer look at Markov models, which are the most commonly used models in health outcomes research. Two examples of individual-level models are Markov models, which can also be designed as individual-level models. As mentioned in the previous slides, these models are static in nature. Another example of individual-level models is agent-based simulation models, which are dynamic in nature. This concludes section 1 of this lecture. Now, let's test your knowledge with a quiz.